Hi everyone, today I will present the paper multi-layer packed classification with the graph processing units. This paper studies how GPUs can improve packed classification in software based NAT switch packed classification maps incoming packed with network rules. Unlike CPUs, GPUs contain many papillary cores that can process multiple packets at the same time, improving speed and efficiency. Then the authors process GPU-based classification methods and a system called G switch to optimize packet processing. The results show that GPU-based solutions achieve much higher performance than traditional CPU-based approaches. 2. The slide shows the presentation outline. First, I will explain the background and motivation of the study and why GPU isolation is useful for packet classification. Second, I will briefly introduce the GPU archive culture used in the paper. Third, I will discuss the three GPU-based classification algorithms: linear search, tube search, and plum search. Fourth, I will explain G-switch, the GPU asserted software switch processed by the athletes. Finally, I will present the experimental results and the main conclusion of the paper. This section introduces the background and motivation of the paper. Packet classification has become more complex in modern networks due to virtual switch SDN and large rules tables. Network device must process packets quickly while checking many rules at the same time. The authors suggest using GPUs because the proved high parallel processing power and can improve packet classification performance. However, GPU algorithms must be designed different from CPU algorithms to achieve the best results. 4. This slide explains the motivation and contributions of the paper. In virtual data centers and SDN networks, packet classification becomes more complex because of large rule tables and multiple hard floods. Traditional CPUs have limited power slim, while GPUs can process many packets simultaneously. The paper processed three GPU-based classification algorithms: linear search, tube search, and plum search. It also introduced G-switch, a GPU-assisted software switch. The results show that the GPU solution is significantly faster than CPU-based classification and can achieve up to 10 GPP throughput. The design focus on efficient memory access, shared memory used, and full GPU allocation. 5. This solved reviews previous search related to GPU based packet classification. Previous systems such as packet shared and GPU metagramming use GPU as to accelerated packet processing, but the manually related online search, which becomes less effective efficient as the number of rules in graphs. The main contribution of this paper is the introduce of a Plum search, which use Plum filters to reduce unnecessary searches and improve prominence. The results show the process approach achieve high throughputs and better efficiencies than preference GPU-based solution while using only a singular GPU. 6. This section introduced the GPU architecture used the paper unlike CPUs. GPUs contain many parallel across and high chiller memory systems. The performance depend on events, memory access, and keeping the GPU cross filled at last. The paper used the NVIDIA GTS 5080 as the tracked platform, and the next slide explain its architecture and the key factors that affected backed classification performance. 7. The slide explains the architecture of the NVDA GTX 58 GPU. The GPU contains 60 multi-processing with a total of 12 processing cores that can execute many thirds in Paler. It also includes different memory levels, with shared memory playing an important role in speeding up packed classification. The GPU works by transferring data from the CPU, working by data from processing it in parallel, and then returning the result. Two key factors for high performance are effective memory. A success and full utilization of GPU cores now as occupants. 8. The section explaining the three-packed classification algorithms and implement on the GPU. The first algorithm is linear search, which compares packs with all rules but becomes slower as the number of rules increases. The second is tube search, which groups rules into classes and uses hash tables for faster lookups. The third is the Bloom search. The main contributions of the paper, it used the Bloom filters to quick eliminate non-matching rules and reduce lookup time, resulting in better performance. 9. This cell explains the GPU evolution of the linear search algorithm. The algorithm compares each incoming packet with all available rules to find the highest protein match to improve performance. The rules are loaded into shared memory, and memory SXs are organized in a call set manner. Each GPU third process packed in Pula will atomic max ensures that the highest profit matching rules is selected correctly. Although this approach is simple and benefits from GPU bar slim, its complexity remains high because every packet must be compared with every rule, making it less efficient for large rule sets. 10. The slide explains the type of search algorithm on the GPU. Unlike linear search, tube search groups roles into the classes that share the same marks. Each class uses a Cocoa hash table, allowing back lookups to the document much faster. Each GPU block handles on glasses loads its mask and hash table into shared memory and then checks whether incoming packs match a rule in that class. This approach is more scalable than linear search because it avoids comparing packed with every rule, resulting in faster classification for large rule sets. 11. This slide explains Plum research. The main contribution of the paper Plum search adds the Plum filters before the hash table lookup. Then Plum flats quick and defines glasses that cannot match a pact, avoiding unnecessary and expensive hash table searches. Only glasses that pass the plumb filters and checked in the Kako hash table. This reduce lookup operations and improves performance. As a result, Bloom search is faster than tuple search, especially when the number of glasses is searched and only few glasses match each pact. 12. This slide introduces G switch, the GPU as accelerated software which props it in the paper. G switch combines GPU based packed classification with higher speed packed input and output. It uses PF rank for fast packed processing and CUDA terms for asynchronous GPU exhaustion. The main goal is to overlap packed a slash zero on GPU processing, improving throughput and keeping both the CPU and GPU eventual at last. 13. This slot show the arch culture of G switch. The system use PF rank for high speed backed into and out path while called uh, called terms manage GPU processing packets and collecting in paths sent to the GPU for classification and then returned to the CPU for forwarding. The main idea is to overlap packet A0 with GPU computation, allowing the CPU and GPU to work small charts and improve over switch performance. 14. This section represents the experiential evaluation of the process system. The experiment measure GPU performance date transfer overhead through paths and compare GPU-based classification with CPU-based approaches. Different rule set and network synchros were tested to influence the three agreement and the over performance of G switch. The following slots present the main results and conclusions. 15. This slide presents the GPU micro mark result. The experiments show that the transfer between the CPU and GPU is not a major bottleneck when packed patching is used throughout encourage as the page size grows and reaches its peak performance at around 8K packets per patch. The results also show that the slot's GPU conventure achieves full occupation and eventual at last shared memory which help improve packed classification performance. 16. This slide compares the GPU and CPU performance. The results show that the GPU significantly outperforms the CPU even when all CPU cores are used. The GPU achieve about 7 times higher performance for linear search and up the 12 times higher performance for Plum search. The experiments also show that Plum search scales well as the number of rules increase, manipulating higher throughput even with large rule sets. Overall, the GPU improved better scalability and much higher PEX classification performance than the CPU. 17. This slot analyzed the throughput under different rules, seed combination. The result show that Plum search achieved the highest throughput, special then the number of classification is moderate. Trump Template search performance better than linear search, while linear search remains the slowest. The experimenting also show that throughput is affected by the number of match glasses and the size of packed flask. Similar packed hiders require less processing and through for achieve higher throughput. Overall, Plum search provides the best scalability and performance across different network skinner. 90. This slide summarizes the main conclusion of paper. The results show that GPU acceleration signification improve packed classification for performance and erects the processing bottleneck is software switch among the proposed algorithms. Plum search achieve the best performance and scalability, supporting high throughput even with large rule set. The study also demonstrated that GPU-based solution can be 7 to 12 times faster than comparable CPU implementation, making GPU as a practical and cost effective combination for SDN and software defined network environments. Thank you for your attention.